In this lecture, we're going to go over the use of GDB, which is the standard Unix debugger. And we'll use the attached program bad.c, which I'll run up here as well, as our sort of test case for a GDB debugger session. Note that it does have 3 bugs. First, there's a potential divide by 0 error here in FB. There's a failure to return the result of FB from FA. Line 4 should read return FB BA. And then there is a dereference of a bad pointer down here in FC. Well, imagine those bugs aren't obvious, and we'll use GDB to find and diagnose them. Now, GDB, like any debugger, does the following. First, it lets you run the program under control of the debugger, including providing command line arguments and optional input and output file direction if you want. It reports the source code location of any faults, it's number 2, and lets you display the source at that point. 3, it lets you print the value of variables or expressions at the point of the fault. 4, it shows you the series of calls that led up to the fault. 5, it lets you set breakpoints to stop execution at any point. And 6, it lets you automatically print the value of variables without stopping the code at any point in the execution, in the way you might do by hand with debugging printfs. Now, this topic will cover only lines or only items 1 through 4. Items 5 and 6 are up to you to figure out if you like, but for reasons discussed below, we actually discourage their use. Now, as with any lecture that walks you through an application, it's very helpful for you to personally run the commands we're showing. So please grab a copy of bad.c, start up a Unix session, and follow along as we go through GDB commands, running a GDB session of your own. Now, to use GDB, the first thing we have to do is compile with debugger information. The executable file produced by the C compiler normally contains just machine language. But to track the source code location of faults, to display the source lines in question, to print memory contents based on variable names, GDB requires additional debugging information in the executable. You add such information by compiling with the -G flag, thus. And again, do that yourself as well. And once you do that, the resulting executable has debugging information for GDB to use. And it's also runnable, just like an ordinary executable might be. Although, as we know, it has a few problems. And here's question 1. Try compiling bad.c both normally and with debugging information added. Roughly how big is the debugging information compared to just the machine language? Compare the executable file sizes. And coming back from a pause there, well, if we try it out by doing a GCC the straight way here, and then do an ls-l on a.out to see what we have for size, and then try alternatively with the G flag like that, and do an ls-l of a.out, we can see that it looks like about an extra 1600 bytes or so there. So maybe about a 30% or so increase. Now, your results might vary, but the point is that's real data being added to that a.out file, and it takes a little bit of extra room. Now, once the executable is compiled with debugging information, you run GDB thus, and assume in my transcript that the $sign is the shell prompt, so GDB and then a.out. Now, you give the executable, you see, as a command line argument. This results in some initial banner lines, like these here, and then at the bottom, a GDB prompt right there. At this point, GDB is running and has your executable loaded, but it hasn't started the executable yet. You run the executable with the run command, like that. Your program now runs. As you can see in the behavior of the program, is about as you'd expect. In fact, it looks just as if you were running it independently of GDB, unless, of course, there's a fault. So, let's cause a fault. I'll enter a 0 for the first value, and if you trace the code, you can see it will cause a division by 0 on line 8. So let's just do 05 there, and there we go. What would have been a simple fault without GDB instead becomes a GDB announcement of the fault, including a listing of the offending line. Now, what can we do from this point on? First, we can list the surrounding source lines via the GDB command list. So if we run that here, we get a short listing of the lines surrounding the point of failure. Now, question 2. We can't cover every GDB command in detail in this lecture, so I'd like you to do a bit of external research and determine how you might list other lines of code, other lines of source code from GDB. In particular, what parameters does list take? A hint, by the way, GDB has a reasonably useful help command. So, coming back from a pause there, if you do help list, you get a kind of unclear, but still readable if you look closely, description that shows that you can add line numbers to the list command. So if I want to go from, say, line 7 to line 25, I just do that. And that will list the lines in question. Repeated list commands, by the way, as also indicated in the docs, will show you successive lines of code. If you start with list line 1 and then do list and list, you get kind of a crude scrolling behavior with each list command. Now, what about printing the value of expressions? Remember, we're still at the failure point here. To get the value of a variable or expression, you use print, followed by the variable or the expression. So print C, for instance, shows that the current value of C is 5. Print C plus 42, and that gives, that gives 47. If a bug isn't clear, getting the value of related variables often helps. And in particular, in this case, if I wanted to print C divided by D, you don't end with a semicolon, I see division by 0, which definitely shows me my problem. The print command also saves each expression that you print in a numbered series of registers, so you can fetch the values back again to use them in further expressions. As you can see, our first 2 print values are saved in $1 and $2. So, for instance, we can reprint those or use them in other expressions. Print $0 gets me a, $1 I should have said, gets me a gets me a 5, and print $1 plus 42, say, gets me 47. And of course, those new values are also saved as registers. Now, it's also useful to know what series of function calls led up to a bug, and what the parameters of the calls were. To get a complete stack trace of all calls leading to the failure point, use where. This lists in top-down order each current function call with parameter values and the source line making the call. Let's try that here, and we can see that main called FA, and that in turn called FB, and the parameter values are listed right here as well. Now try this yourself. Restart the terminated executable with another run call. Say yes when it asks if you want to restart the program. Then exit the scanf loop in run.c by immediately giving an EOF. Diagnose the fault that now occurs. It'll be in a different function. And in particular, what line does it happen on? What value got passed to FC? And what happens if you try to show the value of P? What about star P? So, coming back from a pause, we do a run. Yeah, we want to restart. And then to end the input, I do as I would in the shell, just Control-D. And I wind up with a fault here on line 14. So, and a where command shows that a large random value is passed to FC. because X was uninitialized in the main. Now, printing P shows that it contains the address 3, which I accomplished with some rather nasty pointer casting there on line 12. Printing star P indicates that that's memory it cannot access, thus the seg fault. Okay. A quick question on something mentioned briefly before. Use help run now to find out how to run the program under GDB with command line arguments or with redirection of input and output. Coming back from a pause, help run, in its kind of nerdy little description here, indicates that you can add arguments and that you can also use less than or greater than. So we could, for instance, do a run and arg1, arg2 if our program took command line arguments, and less than some input file and greater than some output file like that. I won't run that because it wouldn't make sense in our current context, but that's available if you need to test using input and output redirection. And then a final quick point, to get out of GDB, you use quit. And you can do that from any point, even if a process is still running, as ours is at its fault point. So we just give it a confirmation there. Now let's close with a bit of discussion on the best use of debuggers. Proper use of debuggers will save you a lot of time. A debugger is much faster than using debugging printfs in many cases, and being able to quickly get the values of a few variables surrounding a fault and the chain of calls that led to the fault is useful. But it's easy to become dependent on a debugger and suffer what we might term debugger hypnosis. The hallmark symptom of this is that you spend more time communing with the debugger, setting up elaborate breakpoints, poring over dumps of traces, etc., than you do looking at your code. And this can happen with debugging printfs too, of course, but debuggers make it a lot easier to fall into this trap. You'll find bugs more quickly and get better at bug finding if you get just a modest amount of help from the debugger and do the rest by reading and thinking about your code. And there are two other important reasons for not becoming dependent on a debugger. First, in practice, some bugs happen only after significant runtime. While you can get stack traces and a few variables of interest at the point of failure, you cannot trace point your way into the failure when it takes minutes of runtime to reach it. And even worse, some bugs happen only intermittently under load. Websites in particular are famous for this. You can't use a debugger to find those. And second, especially in C, some bugs do not even show up under testing, at least on the system in question, and they only show up after porting or other code modifications. Did you notice that the missing return here on line, this was about 4 or so of the program, do you notice that that never caused a problem? Well, that's because it accidentally happened that the return value from FB went in the location that FA's unsupplied return would have gone. So it is as if line 4 had said, return FB, BA. But that will break as soon as you move the code to another machine. Indeed, it may have done so already on yours as you tested along with me. The debugger can't help you find that one. You'll only find it by reading your code. So, use GDB to about the extent we have in this example, but don't become more dependent on it than that.